Okay, so we're going to take a look at Theorem 5.3.1 of the textbook Dynamical Systems by Brin and Stuck. Okay. This theorem states that if we have a hyperbolic set, so remember that a hyperbolic set of this function f from u to m, where m is a C1 Riemannian manifold, this is a compact set which is invariant under f, and we have this constant lambda and families, a decomposition of the tangent spaces, a continuous decomposition of the tangent spaces into stable and unstable tangent spaces, which decompose the tangent space at every point. And we have that f is a contraction, a strict contraction in the stable manifold. When restricted to the stable manifold, the differential of f, I should say, is a strict contraction, and the differential of f is a strict expansion when restricted to the unstable manifold. Okay, and these are continuously varying families of subspaces, and we furthermore require this invariance, that the differential of f preserves this stable tangent space, this a stable subset of the tangent space, and the differential also preserves the unstable portion of the tangent space. So this is the invariance of these of this decomposition into stable and unstable tangent spaces, the invariance under the differential of f. Okay, so we're given this hyperbolic set lambda, and the theorem states that we can find an open set O in U containing lambda and a positive epsilon and delta naught with the following property. Okay, so for every epsilon greater than 0, there is a delta greater than 0, such that for any g from O to m with this one distance between g and f less than epsilon naught, so I'll quickly go on a tangent to explain this distance. Okay, so if we find a g close enough to f, in particular, it needs to be close with respect to this one distance. Okay, one distance, I wrote it down here. So essentially, the one distance between g and f is defined as the zero distance between the differentials. The zero distance can be found on page 140 of the textbook. And I'll put a link for the textbook in the description. So this distance, this zero distance between these differential maps, well, these differential maps are maps from the tangent bundles of x, the tangent bundle of y, and we're equipping the tangent bundle of y with the Riemannian distance, which is induced by the Riemannian metric on y. So we have a natural notion, we have an inner product at every point, and so we can define a geodesic distance and essentially define the distance between 2 points of ty through parallel transport. Okay, so but that actually isn't going to be a problem here, because we're just taking this minimum of the number 1 and the supremum over every point in the tangent bundle of this distance between the image of the vector v under the differential of x and the image of the vector v under the differential of g. Okay, and so this distance is going to be well defined on the tangent bundle, because we know that we have an inner product because we're working in a Riemannian manifold. Okay, so that's this one distance, and intuitively speaking, it's kind of measuring this distance between the differentials, right? So we kind of want, we're perturbing f in such a way that the differential mappings df and dg are similar. Okay, and then given any, so for every epsilon greater than 0, there's a delta greater than 0, such that for any of these g's, which are epsilon naught close to f with respect to this one distance, and for any homeomorphism h from a topological space x to itself, and any continuous map from that topological space into O, which satisfies this property such that the pullback of h under this continuous map phi is delta close to the pullback of the map phi under G, okay? And so if you have, and I'll show you a figure of this in a moment, then to kind of help this make more sense. So then there's a continuous map, phi, which actually conjugates perfectly. So phi composed with h is equal to g composed with phi, and furthermore, the distance between this original continuous map phi that we started with and our var phi here is within epsilon. Okay. So essentially, we can find a var phi which is close to this continuous map phi. Okay, and such that this var phi is actually a true conjugation, okay? And var phi is unique also in this delta naught sense, such that if there's another map which conjugates h and g in this manner, then such that its distance from this original function phi to its zero naught distance is less than delta naught, then we must have that it was equal to original var phi function. Okay, so this is a uniqueness claim at the end of the theorem. Okay, so I just want to kind of show you a visualization of what this theorem is saying. You write out all the different mappings. So, okay, so we start with a map f from U to M. Okay. And then we essentially, we look at a continuous map G from O, which is this open subset of U, into M, and G is somehow close to F, okay? So in particular, G is close to F with respect to this one distance, so the distance between their differentials is small, okay? And it's less than epsilon naught. Now remember that epsilon naught is something that we're saying exists at the start of the proof, okay? So basically epsilon naught is attached to the existence of this open set U, okay? And so is delta naught. Okay, so for any map G, which is within epsilon naught of the one distance to F, okay? And any homeomorphism H, so any homeomorphism H from this topological space X to itself, if we have a map phi which goes from X into U such that the zero distance between phi composed H, so this composition, which is secretly a composition into M because we're going to go from H, we're going to go along H, then along phi, and then we're going to include that into M, okay? So this map is close in the zero distance to G composed phi. So this mapping, that's this distance here, okay? So we're saying the distance of phi composed with H, but the distance between phi composed with H and G composed with phi is less than delta, okay? So if we're given this map phi, then we can produce a map var phi, also going from this topological space X into O, such that actually this conjugation is exact. So the map from H through var phi into O and then included into M is exactly equal to the map from phi and then composing with G into M. Okay, so these maps are exactly equal. And this is going to lead to what's called a shadowing lemma, which we can just go ahead and look at. Okay, and then the last thing about this construction is the uniqueness part. And furthermore, okay, I should mention also that this map that we've shown existed, this var phi map, is epsilon close to this original phi map, okay, with respect to the zero distance. And this holds for any choice of this phi, so long as phi is chosen, again, such that this conjugation by phi against H and the map G, okay? This conjugation, so these two, if you pull back H by phi or if you pull back phi by G, then their distance is less than delta, okay? And their zero distance is less than delta. Then for any of these test functions phi, we can produce a unique in the following sense with respect to this, with respect to a delta naught ball around the original phi. So delta naught ball around the original phi in the zero distance, there's going to be a unique var phi in that ball. which perfectly conjugates the maps in the following way that I've boxed in red, okay? Right, and this is going to lead us to something called the shadowing lemma, which let's see if I can find it. So, okay, this is a corollary. It's called Anosov's shadowing theorem. So given a hyperbolic set, for every epsilon greater than 0, there's a delta greater than 0, such that if xk is a finite or infinite delta orbit of f, so delta orbit meaning that that this distance between, delta orbit means that the distance between xk plus 1 and f of xk is less than delta for all k, all right? So this is the meaning of a finite or infinite delta orbit of f, and the distance between this orbit and the hyperbolic set lambda is less than delta for all k. So this entire sequence stays within delta distance of the set lambda. Then there is an x within this lambda epsilon, so an epsilon neighborhood of lambda, I believe that should be. Yeah, so lambda epsilon is the open epsilon neighborhood of lambda, okay? So that we can find a point in this open epsilon neighborhood of lambda such that this point, when it undergoes the true orbit of this point under f, okay, the true orbit of this point under the map f stays epsilon close to this shadow orbit, or this delta orbit xk, okay? And it stays epsilon close throughout all iterations, okay? So essentially this orbit, this true orbit, which is the orbit of the point x, which belongs to the epsilon neighborhood of this lambda, stays within epsilon of this delta orbit, which is somehow close to an orbit of f, in the following sense, that essentially the distance between every point in the sequence and the image of the previous point of the sequence under the map f, that distance is less than delta. So if you fix a point in the sequence and then you move, here's xk, and then you go to the next point, xk plus 1, but you can also apply the map f. And this operation will have an error which is less than delta for all xk. So it's kind of a stepwise error in your approximation. This is easier to verify because it's stepwise, but then turns out that for any of these kind of delta orbits, we can actually find, in a hyperbolic set, we can find a true orbit of some point in an epsilon neighborhood of this hyperbolic set, which is epsilon close to this delta orbit for all k. So it's kind of a very beautiful and powerful result, and it's a direct corollary of this theorem, which I kind of tried to explain, although probably could have done a better job. This theorem 5.3.1 here.